today I'm going to wrap up steady state linear transport, which is kind of where we ended last time. And then we're going to move into non-steady state systems. We're going to jump back to fluid circuits to introduce it and introduce the idea of exponential decay and work a little bit with those equations. And then where we're going to be doing the majority of our work in DL and FNTs and your next quiz will be in the context of circuits and capacitors. Yeah?
Is the next quiz the next Friday?
No, you have 2 weeks until the next quiz. Yeah, so next you have a week off from quizzes next week, which is, I think, good because we're about to peak kind of mathematically for the quarter. I think this is exponential decay is the most mathematically intensive part of this. You don't need calculus. You don't need to do a ton of even algebraic manipulation with them. It just, exponentials can be a little tough. If you are not super comfortable with them and after today you're still kind of struggling with it, like with a lot of topics in this course, I recommend just Google a couple YouTube videos, take 5 or 10 minutes, and just have different people explain them to you. I mean, your TA too. There's a couple key things we need to know about them, and a deeper understanding of like how it's all working is obviously helpful. But if at the end of the day you just need to say like how did we'll get into the specifics. But exponentials are tough. I don't expect you to master them right away. And your level of mastery does not need to get that high. After this, if this all makes your head spin or you're good at it and you just hate it, whatever, we're going to pivot hard into vectors and completely different physics than what we're doing now. So it's a nice chance to refresh, restart for the quarter, both content-wise and grade-wise too, if this stuff hasn't been your strongest. All right, so steady state linear transport. This is the general model that we've been talking about for the last bunch of weeks. We started talking about it with fluid, and then we moved on to electric circuits, and then last week and in DL you've seen with temperature and with concentration gradients. But at the end of the day, all of these work by you have high over here, low over here. There's a flow in between. With fluids, it was high pressure. Fluid flows from high to low pressure. Electric circuits, charge flows from high voltage to low voltage. Heat flows from high temperature to low temperature. But all of these systems can be described by this simple model where you have some delta phi, or our gradient, which is just the difference, right? That's our delta P, our delta V, our delta T, whatever. And the greater that difference is, the greater the flow from one to the other, right? And then there's resistance opposing that. So greater resistance, that lowers the flow, and we have this simple relationship that we've applied to a bunch of different systems. However, now what happens if that delta phi is not constant? So far we've just looked at a pressure change that's constant or a voltage change from a battery that's constant, and while the system is dynamic, it's not really dynamic, but things are flowing, right? Fluid's flowing, charges are flowing, but that behavior is constant over time. Now we're going to look at what happens if it's not. And I think the easiest way to at least intuitively see that is with a heat flow situation. We have a hot reservoir and a cold reservoir. We know that as a result, heat is going to flow from hot to cold, from high temperature to low temperature through the medium in between them. And the greater that temperature differential, the higher the flow between the two. However, we know that not everything in nature, really nothing in nature, is like a true reservoir like this, where this temperature differential is going to be constant. If I take heat from the top and I put it in the bottom, in the cold reservoir, both of those temperatures are going to change, right? T high, the hot one, is going to go down, and T low is going to go up. They're going to come meet in the middle, right? And if it's that temperature difference that's causing the flow of heat, then that flow of heat is going to change over time because the temperature difference is going to change over time. So we have an equation here for our flow power. Here it's just the power because it's the flow of energy, but that's the same as I for other situations, is related to delta T and resistance, of course. But if our delta T is greater, we have a greater flow rate. If our delta T is smaller, we have a smaller flow rate. So as that delta T shrinks and these both come toward an equilibrium temperature, our flow rate will also go down. And then after a long time, they'll both be at the same T mid, some temperature in between whatever T high and T low was, and there will be no more flow of heat because delta T will be 0, and there will be nothing left to equilibrate. So our flow rate is actually changing over time, which is something we have not seen before for our steady state systems. So these systems are decidedly not steady state. Okay, so we're not going to work much more with temperature. So let's apply it to a fluid circuit where we're a little more comfortable with the math. So in this case, I have two standpipes we've seen a lot connected with a pipe at the bottom that has some resistance. One has a higher water level than the other, and so we know what happens is that the water flows from one to the other, right? The water levels come to balance, and as time progresses, they equalize. So let's write out Bernoulli's equation for each one of these snapshots. So Bernoulli's equation has no time dependence in it, right? It's just for steady state, it's supposed to be the same over all time. But it turns out we can use it, like I said, for snapshots like this. We can describe Bernoulli's equation at this instant. We can describe this setup with Bernoulli's equation at time t, and then at separate time t, but they might be different equations. So for our initial state, where we have two different water levels, we have delta P plus delta P over volume, rho G delta H equals minus IR. We'll say no change in kinetic energy. Well, the way I've drawn it, you could say that there is, well, actually, no, there's not. I've missed the most important step. What was I thinking? What's the first thing we do when we're trying to write Bernoulli's equation? What do we need to decide before we write it down? Does anyone remember? We need to decide our start and end points. Right? I didn't even make that clear. I just said, let's write it down. Let's say our start point is the top of one fluid column, so the surface of one, and then the end point is the surface of the other. Now it's clear why we didn't write kinetic energy density out, right? We have a delta P, whatever, some change in pressure. There's some rho G delta H, because those two water levels are different, right? The columns are of different heights. And we have some IR, because we said there's resistance at the bottom. But we don't have a change in kinetic energy density, because looking only at our start and our end point, those two have the same cross-sectional area. So that's why we can ignore it. But either way, we have some pressure change, we have a change in potential energy density and resistance. However, what do we know about the pressure at the top of both of these fluid columns? It's in contact with the air, so those are both at PATM. Regardless of what their height is, at the top of the fluid column, we have PATM for our pressure, and so our delta P is just PATM minus PATM, or 0. They're at the same pressure. So how is their flow? Well, rho G delta H is not 0. Right? There is a difference in potential energy density from the higher side to the lower side, and we still do have this resistance term, so we just have the interplay between that. The driver of the flow is this difference in potential energy density, and the flow rate is then determined by that and the resistance. Now let's take a look at our equilibrium position, which happens some amount of time later. Current goes to 0. We know that, right? Because once the fluid columns reach equal heights, they're not going to keep flowing, right? It's not just going to keep going until the other side is completely full and one's empty. They'll just come to equilibrium. And if they're in equilibrium, then there's the flow rate we know is 0. Just intuitively, we know if the water levels aren't changing anymore, there's no flow in between them. So if delta H, well, I mean, we can kind of derive that. Delta H in this scenario is 0. So looking at our first equation here, delta P is still 0 because they're both, the top of the fluid columns are still both at PATM. So our delta P is 0. Our delta H has gone to 0 because they're at the same height. And so our current must also be 0. We could also work in the opposite direction, saying at what height does the current get to 0? So like what height difference between the two? When will this system stop evolving? Well, if I plug in I equals 0, the only way that can be true is if delta H equals 0. So in this case, it's like pretty intuitive. We just know what's going to happen. The fluid columns will, like there will be flow until they reach the same height, but we can argue that using Bernoulli's equation that current goes to 0 when the heights are equal, or when the heights are equal, the current will be 0, either one. So we have two different snapshots that Bernoulli's equation describes well, but we want to look at what's happening in between, right? How long does this take? Does it happen at a constant rate? So on and so forth. So we're going to need more machinery for that. But real quick to check in, which system will have a larger flow rate? So we know that there is some flow at the beginning when they have separate water heights, and then once they come to the same height, the two columns, we have a delta H equals 0, there's no more flow rate. What about from when we start to like halfway through? So some of the fluid has flowed from one side to the other. Which system has a larger current? Yeah, exactly. We can say just our intuition kind of tells us that, right? If we have two water levels, one's much, much higher than the other, it's going to push the water across really fast. Or we could argue with Bernoulli's equation. In this case, the delta PE over volume, right? The potential energy difference is really big, so they're going to equalize faster. But yeah, the current is greater when the delta H is greater. And as the delta H decreases, the difference in height, the current goes down as well. So that's how we start with some initial current, they come closer and closer to equilibrium, and as they come closer to equilibrium, the current decreases until it reaches 0. And that can all be explained by the equation we found before. Delta P term goes away because they're always at PATM, both of them. So the pressure is the same, but we just have this delta H being proportional to I, or negative I guess. Okay, so we have something interesting going on here. The current is changing over time, and it's decreasing from some value to 0. Let's take a look at another scenario with a fluid circuit. This case, we're just kind of going backwards. Instead of having two unequal height standpipes connected with a pipe with resistance, we're going to take two with equal height, so they're starting at some equilibrium, and we're going to put a pump in the pipe in between them. So now we're going to force them to grow apart instead. So what happens over time is that the water level in one rises and the other one shrinks, right? They grow away from equilibrium or their original equilibrium value, but we're still going to reach a point where the current goes to 0. Why? Well, the pump only has so much energy density to add, right? If we think of it as a budget again, the pump gives some energy density to the fluid as it flows across, but then as it goes up and up and up, as the water level rises in that standpipe, we're spending it on potential energy, and eventually we're just going to spend it all. So the stronger the pump, the higher the water level will rise, the greater that delta H between them, but it can only go as high as the pump can support. And we can say that using Bernoulli's equation too. Same equation we had before, except I've added the E pump term. We also have resistance still. Now, for our initial state, like always, our delta P is 0, because they're all still open to the atmosphere, so PATM minus PATM is 0. But also now, in the starting point, delta H is 0 too, because they start at equilibrium with the same height. So now our Bernoulli equation for the start of this is just 0 equals E pump minus IR. That looks a lot like an electric circuit, right, where we just have a battery. So if you think of E pump as epsilon, or just like the voltage of a battery, and then we have minus IR, it looks very similar, right? The pump is the battery that's pumping the current through, providing the energy density difference from side to side, and then some resistance is resisting the flow. But then, as the water levels change, delta H is not 0 anymore, right? We started with delta H equals 0, but then that term becomes positive, non-negligible. And then eventually, I will go to 0, right? Like we said, it becomes harder and harder for the pump to pump, and the flow rate will stop. And so we started with just E pump and minus IR, and then we end with just delta H and E pump. Now there's no flow rate, but this equation shows us that it will come to equilibrium when we have a balance between E pump and delta H. Right? The stronger the pump, the higher that delta H will be when they reach equilibrium, but we can only pump so much water so that the height and the difference in potential energy density is equal to the energy density added from the pump. Okay, so let's take a look at, again, how the flow rate is changing in between. We have some flow rate decreasing to no flow rate. So that's one thing I guess we figured out, is that the flow rate in both of these scenarios starts at one thing. We have some flow that's causing the circuit to evolve, and then that fades away. Okay, so looking at this pump scenario where the pump causes the water to become not equal, we found that the flow rate depends on delta H. More specifically, as delta H increases, the flow rate, I, decreases. Right? The greater that difference, the lower the flow rate, because it becomes more and more difficult to pump more water over to the left as the potential energy density difference increases. But the other important thing, the connection we haven't made yet, is that the rate of change, so how quickly delta H changes, is directly related to I. Right? Delta H, the height of the water, think about a graduated cylinder with a bunch of markings on it, 10 milliliters, 20, up to 100, whatever. But you read the volume on a graduated cylinder by looking at the height, right? I mean, it's just geometry, just the volume of a cylinder. It's a function of the height, right? The cross-sectional area is not changing. So the higher the water level, the more volume in the pipe. And what is current? But it's a flow of volume, right? So the flow of volume is what's causing the height to increase. So if we're saying that our current is decreasing, the amount of volume flowing through per unit time is going down, then the rate that the height is changing is also going to go down, right? If I start with, 1 meter cubed per second, and then we're saying that that's going to decrease over time down to 0.5 meter cubed per second, at that later time, H is also going to stop moving as quickly. It's going to slow down because less fluid is going from one side to the other. So it's kind of like a feedback loop, if you want to think of it that way, where as delta H increases, I goes down, and then as I goes down, the rate of change of delta H goes down. So what do I mean by rate of change? We'll talk about it graphically in a sec, but it's delta H over delta T, really your change in height per unit time. How quickly is that height changing? So logic we found here, larger difference in height means a smaller current, means a smaller rate of change of height. So if we go from start to finish, what we figured out was that the rate of change of our height difference depends on the value of our height difference. Yeah? Nope. No. So once we kind of introduce exponentials, then we'll see how it can apply to any arrangement where the delta P or delta V or whatever is not constant. Good question. So the rate of change of H depends on the value of H. So if we were talking about, that concept you can apply to anything. The rate of change, how quickly something is changing, depends on, if it depends on what its value is, it's an exponential. So I don't know. We'll maybe just go to the next slide. But the same is true for the current. The rate of change of the current depends on the value of the current. And when you see something like that, or when you have a relationship like that, we are going to use an exponential decay to describe it, which I'll walk us through. So we just said a bunch about fluid circuits and found that we have what I'm going to say is some exponential decay relationship where the rate of change of something depends on its value. Now we're just going to talk about exponentials a little generally for a second. So this is I switched to saying y and t, whatever y is. Y could be height, y could be current, y could be charge. We don't know yet. We're just talking straight math here. Some y is a function of t. So at time t, we're plotting y. We're plotting y over time here. So y of t on the y-axis, time on the x-axis. And this is our exponential decay equation that we're going to use a lot and apply to a bunch of different scenarios. And we're going to like swap the variables out. Might not always be y, but it's still exponential decay. So we have y equals y naught times e to the negative t over tau. So let's see what each one of those things really means. Y naught and tau is that little like kind of curly t. Those two things are just constants. And t is, well, it's time. So we can plug in a value of t and get a value of y. And that's how it tells us how y changes over time. So let's try that. Let's plug in time equals 0. So y of 0. If I plug in 0 to this equation up here, this is one of the few key things about exponentials we need to know, is that e to the 0, or e to the negative 0 over tau, which is just e to the 0, is 1. In fact, anything raised to the 0 is 1. So that's a key concept here. 2 to the 0 is 1, e to the 0 is 1. So y0 times 1 is just y0, or y naught, we call it. So at time t equals 0, y of t is equal to y naught. And so we plot that on the graph here. That's our starting point. At t equals 0, at our initial, we start at y naught. That's why we call that value y naught, because it's our starting value. All right, now let's plug in a later time. So now we'll plug in tau. So we don't know what number that is, but I just said it's some constant. So whatever it is, what is y when the amount of time that has elapsed is equal to tau? Well, if we plug in tau here, we get y naught times e to the negative tau over tau, or e to the negative 1. There's another important thing you need to know. E to the negative 1, or anything to the negative anything, is just 1 over e to the 1, or 1 over e. So this is something that hopefully you know or comes back quickly, but like e to the negative 1 is 1 over e. 2 to the negative 4 is 1 over 2 to the 4. 10 to the negative 1 is 1 over 10. So that's how negative exponents work. And so y naught times e to the negative tau over tau, or e to the negative 1, is just y naught over e. E is a fundamental constant. It's about 2.7, I think. So y naught over e is roughly a third of y naught. So far we've figured out at time t equals 0, we have our initial value y naught. After some amount of time, tau, which we don't have a value for it yet, but it's some constant related to whatever we are applying this equation to. After tau has elapsed, we've decayed down to a third-ish, 1 over e, of our initial value. Then let's plug in an even later time. So let's plug in a time t that's huge, and like something that's much, much greater than tau. So we went from 0 to tau, now many, many times tau. Then we get y naught times e to the negative huge number. That means we have y naught times 1 over e to the huge number. That ends up being essentially 0. So that's another important thing here. And a number raised to a very high exponent is just huge. When we plug in a huge value, even if it's 1.1 to the 100th, those exponents rack up real quick. So we're going to get y naught over a huge number, which is essentially 0. So now we figured out y starts at y naught at time t equals 0. After an amount of time tau, we've decayed to about a third of our initial value. And then after many times tau, or after a lot of time, we've decayed essentially to 0. So this is our exponential decay that we're going to see how this can be applied to describe the behavior of but the non-steady state fluid circuits we're going to be looking at. Whether it's those two fluid circuits we just looked at, which this can apply to. It's going to apply to a lot of different situations of electrical circuits. But this is our base equation that will describe all of the different behaviors that we see. Okay, so what is tau? It's the time constant, we call it, and it's a characteristic time scale for a system. So what does that mean? Well, just physically, mathematically, what it means on this graph is it's how long it takes to decay to 1 over e of our original value, or about a third of our original value. So this could be 1 second, which tells us that our system decays on the time scale of seconds, right? It tells us that after a second we'll be at a third decayed, or 2/3 decayed, like down to a third. And then after 3 or 4 seconds we'll be essentially at 0. Tau could be an hour, which tells us that our system takes an hour to decay to like a third of its original value. And then, in 4 or 5 hours, whatever, it'll be down to 0. So tau really just sets this characteristic scale for the time evolution of our system. We still have the same shape, but it's a different scale. And those we'll do more work to see like what things about a circuit affect tau, but it's just related to the things in the circuit. It could be resistance, it could be gravity, it could be the density of the fluid, area of the pipe, whatever. But these are the physical traits of the system that we're trying to describe, determine tau. Right. The other thing that we found, or that I've noted on here, is the steepness of the curve and how it changes over time. So not only are we decaying from some value down to 0, the rate of change of that decay is changing. What physical marker am I looking for rate of change? It's written up here a lot, but when you hear rate of change and you want to look at a graph, what thing about that graph is the rate of change? It's the slope, right? And you can see here, at early times, so close to our starting point, we have a very steep slope, right? A small amount of time causes a large change, a lot of decay. It's a very steep slope, and then over time, that gets shallower and shallower. So you could kind of prove that to yourself when you take, like, slope is also the derivative of something. We're not going to do that in this class, but if that means something to you, then great. But really what we're seeing with this exponential, which is plotted out here, is that the exponential, the slope of it decays over time as well. So our actual value, whatever y is, has some start and it's decaying to 0, but something else is decaying too. It's its slope. Its slope starts at some large value, or here it's very negative, but then it decays away to a shallower and shallower as it asymptotically approaches 0. So we have two kinds of decay here: decay of the actual value and a decay of the rate of change. So this kind of ties in like why we needed this in the first place. It's the rate of change of y, or the slope of this curve, depends on the value of y itself. Right? So if I pick a y value, that tells me also what the rate of change will be there. And here, the lower the value of y, the lower the rate of change of the curve at that point too. Okay. Also, tau kind of marks out the delineation between steep and shallow. What steep and shallow mean depend on what your constants are and stuff like that, but you can just see visually. When I plot this out, times before tau show a very quick, rapid decay, and times after tau starts to slow down a lot. So again, it's going back to this idea of just like a characteristic time scale. Specifically, it tells us how long it takes to decay to 0.37 times its original value, but it's a very useful piece because it's easy to find in an exponential. You can just read it off from the equation, and it just gives us an idea, right? Is it seconds, minutes, hours, days? How quickly is our system evolving? Okay, great. Any questions about just like the math of exponentials real quick? Again, I recommend just like do a little review, watch a YouTube video, write it down a couple times, but this is something that we'll need to be comfortable with, at least just plugging in a value for t and seeing what we get out of it. And like another thing that we've done a lot in the past is like asking yourself questions like, if I were to increase this, what happens to the value of this? So you should not necessarily right now, but say like, oh, if I increase tau, what's going to happen to my value of y? Something like that. So you just need to be able to reason through how an exponential works a little bit. All right. So now we have this nice curve, and we have the original system that we were trying to describe. So let's see how we can match them up. How does this curve, this exponential decay, describe something about this fluid circuit? And we're going to try to describe, like I've written here, the current, I, the flow rate. So I've just taken y, which before was just some general value. It's like this is how an exponential decay works. Some value y decays. I've substituted specifically in current. So I'm saying here that the current is decaying over time, which is what we found with this fluid circuit, right? So I guess I'm kind of giving away the answer, but I already wrote it up chronologically. At A, the water levels are equal, right? So the pump can freely pump water from one side to the other. There's no potential energy difference to overcome. So there's the highest flow rate that we'll have. That's our time t equals 0, I naught. That's our starting current. But after some amount of time, we reach point B, where some height difference has developed. There still is current that is flowing from one side to the other, but it's lower because now the pump has to overcome this potential energy difference, right? So the current has lowered a bit. The flow rate has slowed. And so point B is going to occur somewhere in the middle here, where there still is a flow rate, right? Current is some positive value right here, but it has decayed a bit. Then point C, that's where we've reached a level that the pump provides an energy density that is equal and opposite to the potential energy density change, right? So now the pump can't pump any more water from one side to the other because it can't overcome any more potential energy, and so our flow rate has decayed down to 0. So that's how we've matched up this situation here where a pump pumps water from one side to the other, and the rate at which it does that slows over time until it gets to 0. This plot describes that well. And it also shows us, or describes, depending on whether we're arguing this equals that, or like left equals right or right equals left, but it shows us that not only is the current decreasing from one value down to 0, but that the rate at which it's decreasing is decreasing as well. So it starts off approaching 0 very quickly, and then as we get closer and closer to 0, or closer and closer to the maximum height difference, that current asymptotically approaches. So I said we could try to do this for a bunch of different values. Here I plotted the current, which it makes sense, it does decay away. What about the height difference? So same scenario, exact same one, except now we want to describe the difference in height over time. Can I use the same equation that I used before and just swap in h? I'm going to say no, because current did decay away, right? Current, we started with our maximum value, and it goes down to 0. But height difference, in this case, starts at 0 and goes up to its maximum value. It asymptotically approaches whatever its final value is. So this equation is not going to work, because this equation describes starting at h naught and then decaying down to 0. So it doesn't work. We know that the rate of change of h decreases. Well, so I guess these are kind of, I'd want to say them backwards. H increases over time. That's the difference. However, the thing that tells us that we still want to use some sort of exponential decay is that the rate of change of h still decreases over time. So we said with current, sure, current decreases over time. That decays away. But the really interesting part is that the rate of change of current decays over time, right? Remember, at first it was changing really quickly, and then changes slower. The same thing is true about height. Even though height is growing, it changes really quickly at first, because our current is large, right? Remember, like, current is what causes a height change. Early on, there's a lot of flow of fluid, and so the height changes quickly. And then as the current decreases, the flow rate decreases, that change in height changes slower. So there still is some decay here, and I think that's the best way to think about exponential decay. Exponential decay does not necessarily mean that the value that we're looking at is decreasing down to 0. It means that its rate of change is decreasing down to 0. Like you can think of the system as slowing down, asymptotically approaching equilibrium. It doesn't matter if it's approaching equilibrium from the top down or from the bottom up, but it's slowing down to a halt. So the simple swap that we're going to make for this equation, or addition, is that instead of doing h naught times e to the negative t over tau, we do h naught times 1 minus e to the negative t over tau. You could just take it as a given that it works, but another way to think about it is just the expression e to the negative t over tau. Its maximum is 1, and its minimum is 0. At time t, if you just take e to the negative t over tau, if I plug in time equals 0, I get 1, and if I plug in time equals infinity, I get 0. So no matter what, that just decays from 1 to 0. That's our decreasing. But when I do 1 minus that, it's the exact opposite. If I plug in t equals 0, I get 1 minus 1, so now it starts at 0. And if I plug in t equals infinity, I get 1 minus 0. So then this one instead goes from 0 to 1. But that key behavior is the same, where I have a steep slope, and then it starts to get shallower and shallower. The rate at which it's approaching equilibrium shrinks. That's our decay. The rate of change of h is the real thing that we think of when it's decaying. When to use this and when to use the other exponential, that just kind of that's a more conceptual question for us. It's just, is this value increasing or decreasing? And, usually if we understand the circuit or whatever system we're looking at, it should be pretty clear. So if I look at going from A to B to C, before I know, okay, I start with my maximum current, and then as I reach equilibrium, the current goes down. So then I want my exponential decay that decreases. What's happening to the height? Well, that one's easier. It's just height difference I can see is growing over time, and so I'm going to use this equation. These are the only two equations we need to know for exponential change, or like the only two versions of exponential decay that we need to know. The increasing version and the decreasing version, and the two key numbers in it are the h naught or I naught or y naught, whatever, our starting value, which could either be the one that, like in the case of current, we start with and then decay away from, or in the case of height, that we grow to, like kind of decay toward. But either way, that's our like reference value. That's our equilibrium or final, or starting value, sorry. And then the other one is tau, which, like I said, is the time constant that determines how long this takes to evolve, what time scale. And that's it. So now we've talked about exponential. Yeah? Good question, because I left it a little bit hazy here. You could do it either way. I think you actually have a problem that maybe asks this of you, but we could talk about the height on the left individually. We could talk about the height on the right individually, or we could talk about the delta h. All three of those things will evolve as exponential decay, and that they will change rapidly early on and then decay away to 0, or like the rate of change will decay away to 0. But let's take a look at this one. If we're looking at the height on the left, in that case, that's growing. So it would look something like this, right? If we look at the height on the right, that's shrinking. So that would look like something else. And if we looked at delta h, it would be 1 minus the other. So the answer is you can do any of them. In this case, I guess I just kind of left it ambiguous. The things that will change would be that h naught and tau, depending on what the system is. Actually, tau wouldn't change depending on which you described it. H naught would. Okay. Questions on this so far? So now we're going to apply it to circuits. We're going to learn about a new circuit element, a capacitor. And I purposefully chose this kind of funky example of a pump forcing water, like forcing two standpipes that were in equilibrium to a new equilibrium, because it's very analogous to the way a capacitor works in a circuit. So I am calling this a circuit. It doesn't really look like a circuit, but we'll get there. But it's just a battery that's connected between two neutral plates. When I say neutral, I just mean there's the same amount of positive and negative charge on both sides. So we're looking at the top piece on the right here. So we have two plates. QR, the charge on the right, is 0. QL on the left is 0. And that's net, right? We have positive and negative charges on both sides, but they cancel each other out. However, since I connect them with a battery, the battery introduces some voltage difference. So now there's an energy density on one side and an energy density on the other, and charges want to flow from high energy density to low energy density, just like we've seen in a circuit, right? I have a wire with a resistor, nothing happens. I hook a battery up to it, and now charge is going to flow through the circuit from high energy density to low energy density. Very similar to the fluid circuit scenario, where we have two standpipes that are happy, they're in equilibrium, right? They're at the same height, there's no pressure difference, no potential energy difference, no flow. And then when I introduce the pump, I introduce an energy density difference, and so the water wants to flow from right to left here. Same thing is going to be the case for the electric circuit. Now the charges want to flow from left to right. The way the battery is oriented, the positive charges are going to be pulled off the right and land on the left as they go from minus to plus through the battery. The result of that, what happens over time, is if I remove a positive charge from the right and place it on the left, now the right becomes negatively charged, net negative, right? If they're equal and I remove a positive, now it's net negative. And if I add that positive on this side, it becomes net positive. And that happens again and again over time. More and more charge gets pulled from one side to the other. And like we'll see why in a sec, but a similar thing happens to the fluid circuit, where that differential makes it harder and harder for the pump or the battery to continue pumping current through it. And eventually it's going to reach equilibrium. But why does a capacitor reach this equilibrium? Why does it slow down over time the way we've seen with the fluid circuit? So my question is, I guess I just answered it, but does the rate of change of the charge difference change? So is this just something that it just pulls constant over time, no change in how much it happens, charge from one side to the other, and that happens forever? Or is that rate of change going to change? Is it going to become more difficult, maybe easier for the battery to do so? I don't know. Well, I do know. And the answer is yes, the rate of change does change. It's going to be an exponential. That's why I spent the last 20 minutes talking about it. So let's look at one plate of one capacitor and see why it becomes more difficult for the battery to pump charge onto that plate. With the fluid circuit, it's pretty obvious, just because, potential energy, or it's obvious with the knowledge we already have, is that as the height grows, the potential energy density grows as well. And so the pump has to support that potential energy difference. So I start with a neutral plate, and I add a charge onto it. Fine. There's no reason that's a difficult thing to do. Now it just has a net positive charge. But now I add more charges. So these popped up in the wrong order, but now let's look at the scenario where there's two charges. What do we know about like charges? They repel. Positive charges repel positive, negative charges repel negative. So if I had one charge on the plate and I add another, now they're pushing each other apart. I add another one on there. Now they're all pushing each other apart, but they're running out of space. Right? I have a plate with only a finite amount of space for these charges to spread out, and they don't want to be near each other. So the more and more charge I put on there, the more and more crowded it gets, and the less they want to be on there. I'm going to have to start pushing them harder to get them onto this plate because they don't want to be together. So the more charge that accumulates on this plate, the harder and harder it is to push more charge on there. Just like when we're pumping water into a standpipe, the bigger that height difference grows, the harder it is to push more and more water up here because the potential energy density is growing, or gravity is pulling down on that water. Same is true for negative. If these were all negative charges, then it'd be harder and harder to remove more positive. Adding a negative charge is the same as taking away a positive charge. The plate doesn't want to become more negative if it's already negative. If the plate's already positive, it doesn't want to become more positive. So the answer is yes, as charge accumulates, the rate of change decreases because it becomes harder for the battery to pump more charge from one side to the other. So there's our story. There's how we get this exponential decay, is because we have a system that's set up, and over time it becomes more difficult to send charge through it, and so the flow rate, the current, decreases over time. So let's talk about how we describe this mathematically. The last step before we can really take an exponential and apply it to this, we need to introduce the idea of capacitance. So just like a battery has some voltage, a resistor has a resistance, a capacitor has a capacitance, which has to do, well, as the name implies, with its capacity to hold charge, which is what the capacitors are doing, right? They're holding an excess of charge, right? We're building up an excess of charge on each one. And the larger the capacitance of a capacitor, the more charge it can hold with the same voltage. Another way to say that is the higher the capacitance of a capacitor, the easier it is to put the same amount of charge on it. So capacitance we call C. That's the capacitance of a capacitor. And let's take a look at these two expressions here, which are the same, they're just rearranged, that relate Q, the amount of charge on the capacitor, C, its capacitance, and delta VQ, the voltage difference between the two plates. So the first one, the charge Q is equal to C times V, delta V. So what that means is the charge on the plate is equal to the capacitance times the delta V. So what happens if I were to keep the delta V the same, or keep the same battery connecting these two plates, but increase the capacitance? So if I increase the capacitance of the capacitor but keep the same battery, increase C here, keep delta V constant, my Q will go up. That's what I said before, that if I have the same battery and I hook it up to a capacitor with more capacitance, more charge will build up on it. It can hold more with the same delta V. If I keep the capacitance the same, so let's say I take the same capacitor, but I apply it to two different batteries, one with a smaller delta V, one with a larger delta V. The one with the larger delta V, the stronger battery, is going to be able to push more charge onto the same capacitor. Right? So it's the same type of relationship we've seen before, where we have some differential in voltage, and then there's two things at play here: how much we can put on there and how much can it hold. Right? If we either increase the amount of charge on something, that makes it more difficult to put more, or we can also increase the capacitance, make it easier to put more charge. These are all things like knobs that we can turn in our circuit. So if we rearrange that, you can see just what is the voltage difference between two plates of the capacitor. Like I said, the more charge that's on it, the greater the voltage difference, and it's actually inversely related to the capacitance. If I have a very small capacitor, so C is very small, that means I need a large voltage difference to support the same amount of charge. So let's say I want to put 10 coulombs on a capacitor. I have two capacitors. I want to put 10 coulombs on both of them. I'm going to need a much bigger battery, a much more powerful, higher voltage battery, to put that same amount of charge on a smaller capacitor, because it's harder to stuff all that charge on the smaller capacitor, right? It has a small capacitance, so it does not want the charge there. It fills up quickly. They get really crowded and are repelling each other, all the charges, and so I'm going to need a stronger battery to put the same amount of charge on it. Okay, so I've said the same thing a bunch of different ways. Hopefully some of that stuck a little bit. So how does this evolve over time? So now we found the battery. We start with two neutral plates, and then over time, a charge difference builds up as we take charge from one side and put it on the other, and we develop a net negative and a net positive. And the greater the difference between those, the harder it is to keep doing so. So let's put it in a circuit. I think now we have all the tools we need to really see it as a circuit. This has looked kind of weird, right? Because we just circuits we've seen as connected, connected loops, right? We've been using a loop rule. We need a loop in order for current to flow, but capacitors we actually don't. The reason being is that they act as kind of charge reservoirs. They don't have like infinite amount of charge, but if you just have two ends of a wire in a circuit that are cut and not connected, you can't do anything with that. There's nothing to pull charge from. But if you have capacitor plates, you have this big piece of metal with lots of excess, with lots of like charge on it. It might be net neutral at the beginning, but there's a reservoir to pull from. I can pull positive charges from this one and put them on this one. And so that's why we get circuits that still behave with a current acting like circuits, despite the fact that they're not technically connected. No current is going between the two plates. It's just starting at one side and ending at the other, and that's fine because we can draw from one and build up at the other. We're adding this place for it to go. So why did I move them and put them together like this? Well, for two reasons. One, visually, it makes it actually look like a circuit, so it's a lot easier to work this way and make it fit into the way we've been thinking about circuits. But also, arranging them like this versus like this with the two plates, putting them together actually increases the capacitance of whatever the capacitor was. The reason being, just like charges repel, opposite charges, we know, attract. And so if I take the plates and bring them together, these positive charges still don't want to be near these positive charges, and these negative charges don't want to be near these negative charges, but these positive charges do kind of like being near these negative charges. So that adds some attraction between the two plates, and so it's easier to hold more charge on there. So yeah, that's an extra tidbit, but capacitance goes up by doing that. So we're often almost always going to draw them like this, and capacitors will just be, that's our new circuit element. We have resistors, the zigzag, and capacitors, which are just two lines of the same length, parallel, next to each other, and a charge difference builds up between them. Now, we've also developed an expression for the voltage drop across them. Before, on the previous slide, I wrote that expression relating delta VQ to C and to Q, and that was just to say, like, what is my voltage difference between this side and this side, right? But now, if I bring them together, I can still evaluate my loop rule just like I did with normal connected non-capacitor circuits, because I know this side has a higher voltage than this side, right? We found what the voltage difference is. So if I go through the circuit, I get a plus epsilon from the battery. I get to my capacitor, whatever its delta VQ is, which I figure out from like charge and capacitance, I have a voltage drop across it, right? Because this side has an excess positive, this side has excess negative. That tells us what the difference in voltage is between them. So I get a voltage drop across here, that's minus QC, and then I get another voltage drop across the resistor, just like in the olden days. So we can still use our loop rule just fine, except now we have a new element, and its voltage drop goes according to this relationship. Great, so now what does that actually look like over time in a circuit? Well, at time equals 0. So rewinding, the capacitor is neutral. No net charge on either side, right? Same amount of positive and negative on each plate. In this case, we go through, do our loop rule. We get, and this is the equivalent of when we were going through, like taking snapshots of the fluid circuit. So now our snapshot at t equals 0, when I first connect it, I get plus epsilon for the battery. I go to my capacitor. There's no charge on it yet. So there's no voltage difference between the two plates, right? There's Q over C is 0 over C, so no change, or no voltage drop, and minus IR. So before the capacitor has any charge on it, this circuit just behaves like a normal battery and a resistor. How is that happening despite this space here? Well, like I said, instead of the current flowing actually all the way around the circuit, we're just drawing it from one side and putting it on the other. And immediately after the circuit starts flowing, charge will build up. And so the behavior is going to change. So that's where we get to this, why we needed exponentials to describe it here, because its behavior is not constant in time. Immediately once current starts flowing, we develop a charge difference or a voltage difference between the two plates. And now we have an extra term in our loop rule where some of the voltage drop is occurring across the capacitor and some is occurring across the resistor. And then far, far in the future, this will be as full as it can. The battery can no longer pump more charge from one side to the other. Current will stop flowing. And so now our loop rule is just epsilon minus Q over C, because I is now 0. So there's no voltage drop across the resistor. So at the beginning, it's like the capacitor is not there. At the end, it's like the resistor is not there. So I'll leave off here, and I'll pick up next week. You have no quiz next week, so enjoy that. Use it to focus on what's pretty tough material. We'll be spending a good amount of time with this stuff.